In the last segment, we talked about the use of electrons for scattering. In this segment and the following segments, we'll talk about how we can use the wave-like nature of neutrons for scattering. So again, this is the same graph we've seen a few times before. For non-relativistic particles, we can relate the wavelength to the kinetic energy. Here's the curve for neutrons, and so for about an angstrom, that's easily achievable. In fact, what kind of number do we want? If we wanted to have a wavelength of about an angstrom, suitable for crystallography, you plug in h over the square root of 2mk, and you get something like a tenth of an electron volt, or equivalently about 4,000 meters per second. Those are easily achievable. So it's not too hard to get a neutron in the right range for diffraction. Most of the X-ray scattering measurements that we've already talked about can also be done with neutrons. You can do crystallography, you can do small angle scattering, etc. There are, again, some relative advantages and disadvantages. Why might you want to use neutrons? An important feature of neutron scattering is that the neutrons interact with the nucleus rather than the electron cloud. So that means that the scattered intensity is isotope sensitive rather than just element sensitive. And it also means that you can measure magnetic structure. You can actually, for example, measure antiferromagnetic structures. You can do inelastic scattering and measure things like lattice vibrations, so-called phonons, quantized lattice vibrations. And the neutrons are, relative to X-rays, penetrate a long way, so you can go very deep into samples. For example, you can go through 1-inch thick aluminum, where you could never do that with X-rays. The biggest disadvantage of neutrons is that it's hard to get enough flux. For X-rays, it's not too hard in a laboratory scale instrument to get quite an intense beam. To get the same kind of intensity, you have to go to some kind of big facility, and we'll talk about the ways that this is done. And even then, you have relatively small number of neutrons and a relatively fat beam, so you need large samples, typically grams rather than milligrams. Another problem is that under exposure to a neutron beam, some samples can become radioactive. And there's also a new source of background that we'll be talking about, particularly in this segment, which is an incoherent as opposed to coherent scattering from the sample itself. I'll remind you that when we were talking about Fourier transforms, and also when we were talking about small angle scattering, we said that the intensity depended on the correlations of the scattering length density. So for X-rays, the scattering length density is the scattering length per electron times the density of electrons, and every electron has the same scattering length. So for X-rays, the contrast is provided by variations in the electron density. Neutron scattering depends on the neutrons interacting not with the electrons but with the nuclei via the strong force. This interaction is isotope dependent, so the scattering length depends on which isotope you have. In fact, it can even be negative. That comes into what happens with the phase of the outgoing neutron. It also depends on the relative orientations of the neutron spin and the nuclear spin, or the magnetic moments. And so that's useful because you can measure magnetic structure, but can also be a source of incoherent scattering. Ignoring the spin part for a moment, if you look at X-rays, the cross-section is just proportional to the atomic number squared. So you just take z squared, and so that says that heavy elements scatter much more strongly than light elements. For neutrons, there's no particular relationship between which element it is or what z it is. It depends on the isotope. So for example, you can see that hydrogen and deuterium, which are two isotopes of the same element, have quite different scattering lengths. And you go from silicon to iron, that's a modest increase for X-rays, huge increase here for neutrons. So if you're not a nuclear physicist, really you just have to kind of look these numbers up. Because that scattering length depends on the isotope and can also be spin dependent, you can get an interesting effect that does not appear in X-rays. If all the nuclei that you were scattering from had the same scattering length, then you could get scattering in phase. You require constructive interference to get Bragg scattering, and so the coherent scattering cross-section, that is to say the part that can give us things like Bragg scattering, just depends on the average scattering length quantity squared. However, if you have a lot of variation, you can get random phases that will kill the Bragg scattering, but you will have basically diffuse scattering going in all directions. The cross-section for that happening depends on something that's proportional to the standard deviation of this cross-section. That is to say, it's b squared average minus b average squared. for most elements, the coherent cross-section dominates. An important example is hydrogen. There, because of spin effects, the incoherent cross-section is much larger than the coherent cross-section. Now, for structural studies, you really want to have the coherent part. So for structural studies, hydrogen is a nuisance. The more hydrogen you have, the more incoherent background you have, and the harder it is to see anything like back scattering. There is a technique called quasi-elastic scattering. If you're just interested in the energy dependence, then you can actually make use of that incoherent scattering. The books by Squires and also by Willis are very useful introductions to this. In the Lindner and Zem book, there's a very nice book on contrast variations and the scattering length density. And I can also recommend this very nice website out of NIST.